Just to quickly go over the outline of what we're going to do on this webinar, we'll start out with a little background on just performance testing options, RFC-2544, ITU Y.1564, and then what the webinar is basically about, the RFC-6349. We'll get into some TCP principles, where we'll go into some interrelationships with how TCP throughput is affected, and as well as some other things related to the TCP and the protocol itself and how it's affected. We'll go over a little bit of what GL hardware platforms are utilized here. Some of you may be familiar with some of our platforms there. Our PacketExpert platform is generally the one that we're using for this ExpertTCP. And we're going to get into exactly how we do our throughput measurement, where it's a three-step process, and we'll talk about how that's done. And we'll end up with some screenshots and a small video to show you the software. So to get started, what are some of the packet Ethernet performance testing methods that are most common used in the industry? That's a question that everybody may have. Some you may be familiar with. Traditionally, RFC-2544 and ITU Y.1564 have been used. These are generally service level agreement tests when the network is turned up or the service is provided. And these are generally used by ISPs to validate or evaluate the service level agreement. These are working at, and I'll get into it a little bit more on subsequent slides, but these are generally at layers 1, 2, and 3. And what we have and what we're going to talk about today is RFC-6349, and this describes the methodology for measuring end-to-end throughput so that we can evaluate the end user experience, the true bandwidth from end to end. And GL's hardware, which you'll see, supports all three of these. So again, here's what we're looking at here with the performance testing methods. The three methods are shown here in relationship with the protocol stack. So as you can see, RFC-2544 and what GL is calling our expert SAM, which is the Y.1564 testing, is generally done at the layer 1, 2, and 3. Those are also done at layer 4, the transport layer, but only with UDP. So the RFC-6349, which is our ExpertTCP, was created to do a true end-to-end user experience TCP test. So this is very useful for ISPs. It can assist them when customers are complaining about download speeds. When a customer generally complains, they're complaining about the download speeds of their applications, so their web surfing or their FTP or their email or something like that. So this is this ExpertTCP and this RFC-6349 are addressing that end-to-end throughput and that true user experience. So typical service level agreements are listed here and shown for you. As you probably know, ISPs offer different grades of service, and this is just a graph that shows you the different grades of service and definitely what's accepted with these service level agreements. And what we'll show here is as an ISP or a network provider will give these SLAs to their customers to truly validate the end user experience. They will need some testing like the ExpertTCP and this. So as we were talking, to give some background on these testing performance, RFC-2544 and ITU Y.1564 are both sort of layers 1, 2, and 3. They do throughput, latency, traditional frame loss, and jitter, and some burst testing. RFC-2544 is a single service test, so a single stream, and ITU Y.1564 expanded on that and has allowed multiple services to be tested simultaneously or one by one. So this is a pictorial of that, graphical pictorial depicting that. And again, we're just trying to give some background here, and then we'll get into how we're doing it. Starting out with RFC-2544, graph here just shows how hardware is configured, and what we're using at GL is what we call our PacketExpert, and it can be set up in basically two ways here: a single-ended way, where port A and port B on the same piece of hardware can be your endpoints, or the test equipment could be on both sides, as shown in the second diagram. And again, these 2544 is a throughput, a latency, and a frame loss sort of test at layers 1, 2, and 3. It does test layer 4 with UDP, but it does neglect the TCP testing, so the true application testing. The next slide is showing a little bit more about ITU Y.1564, which GL is calling that the Expert SAM. And again, this is a multi-service, a multi-stream testing methodology. It's great for SLA validation. Starts by running services in a consecutive order, one after another, and when you can see that in the service configuration test at the top there. And then a second test is basically the services being run simultaneously. Testing similar things to 2544, throughput, latency, packet loss, and jitter. And it's just another, at the same layers that 2544 we're testing. So just another way to validate. The next graph we have and chart is showing the performance testing methods where we've introduced now the RFC-6349 and what is supported for each of these. In general, RFC-2544 and ITU Y.1564 is a good first step in testing the network and validating the SLA. However, these performance tests can be passed with good results, and the end user, the customer, can still complain about performance problems. So they have a slow internet, or that's the traditional complaint. I'm not getting the speed that you have told me that I'm getting. So why is that happening? RFC-2544 and Y.1564 testing may not identify or show that to an ISP. That is why TCP testing, true TCP end-to-end testing is needed. That has been recommended by RFC-6349. And this type of testing will show what the user is truly experiencing, and in the long run for these ISPs and service providers, it's going to save them in costs because they're going to be able to resolve these issues quickly and make their customers happy. Okay, so what is TCP and how is it used? TCP is used if the data delivered from point A to point B, everything has to be delivered. Okay, if it is a method with acknowledgments. Okay, so meaning that if you're just streaming video or you're listening or on a voice call, a VoIP call, UDP is generally used because a packet lost here and there is okay. But this ensures that all packets get delivered from point A to point B, as you probably know. So this is a pictorial of those types of applications. So a customer or a user is at a browser, they're wanting to get a website to be downloaded to them, or they want FTP transfer to come to them. This is showing that, and at the bottom of the screen we're showing how that's been done from a simplistic manner. Data has been asked for, and then an acknowledgement is received. And that is the process for TCP. So the major TCP throughput interrelationships, this slide tries to show you, the relationship between the application, okay, the end user application, and the network itself. So what are those relationships? The bandwidth of the application. How much bandwidth is that application actually needing? That is relationship there. The latency, the delay of the network, the packet loss of the network. These things obviously will affect the performance. The TCP retransmission scheme. So again, this is an application. This is an application scheme that's going on, and that will affect the performance of the user's application. What's the maximum transmit unit of the network? So what's the maximum packet size that can be used in the network? Again, a network parameter essentially. The last couple there are the transmit-receive window size for TCP and the number of TCP simultaneous connections. So how many applications do you have up and running right now? Obviously, some of these things, all of these things will affect the performance that the user is experiencing, as well as, these are the interrelationships between the application and the network. So now I'm going to hand over a couple slides to my colleague Prasad, and he's going to explain a little bit more detail about how TCP works and how this works in the RFC.
Okay, thanks, Matt. Okay, here we explain a concept called bandwidth delay product, which is very important for TCP throughput. In this example, we can see that this network has a bandwidth of say B, and there is an inherent delay to the network, and TCP needs every byte to be acknowledged. So every byte that is sent out should be acknowledged. So there is a round trip delay associated with every byte, because unless the byte is acknowledged, TCP protocol doesn't send the next byte. So it's very important to keep the pipe full to get the maximum throughput, and that is achieved by what is called the TCP windows. So there is number of bytes which are kept ready to transmit, and those number of bytes are pushed to the pipe, so that here you can see that from the first byte till there is an delay for the acknowledgement for the byte to receive on the server side, and for the acknowledgement to receive back to the client. So this delay is the round trip time, and if the window is of such an optimal size that it can push the data till the acknowledgement comes, then we keep the pipe full. So keeping the pipe full is very important in TCP to achieve the throughput because of the acknowledgements. So this BDP is nothing but the number of bytes or the packets in flight, and so more we push in the pipeline, more we can achieve the throughput. If the delay increases, for example, here instead of this first ACK, if the ACK is delayed by this much, then we can't transmit the next buffer, because we have to receive the ACK for this first buffer. So there is a idle time here, then we can't achieve a throughput, the maximum throughput. So the bandwidth delay product is nothing but the bandwidth into RTT, because the buffer and the RTT determines the throughput. So this bandwidth delay product is a measure of the throughput. Okay, so here we'll talk about how the network delay or a misconfigured buffer can affect the TCP throughput. So as you can see in this figure, if the latency increases, then there is a lot of idle time where we are not transmitting. So this the left hand side buffer should be continuous. So now we are not pumping data at the maximum possible, which will decrease the throughput. And also, suppose the buffer is misconfigured and it's not configured to push the maximum that the pipe can handle. Then again, we would have sent out all the packets, and we have to wait till the acknowledgement comes in. So again, we are waiting for the we are sitting idle while the ACKs come in. So both of these buffer size and the acknowledgement affect the throughput. So again, there are multiple factors which affect the TCP throughput. So if now in the previous slide we had a bandwidth, the network bandwidth of 10 Mbps. Now if we have an increased pipe capacity and we are still using the same buffer, so in this case also we are again limiting the throughput, because we are not pushing as much data as the network can handle, and again we have some gaps here which will cause the throughput to come down. So one way of we can utilize this deficiency is we can push more connections here. So in this gap we can have additional TCP connections. So this gap can be occupied by other TCP connections. Then again we can achieve maximum throughput, because here the window size is limited by the TCP protocol to 64.536, that is 64K bytes. So per connection it is limited to 64K. So to overcome that, we can have multiple connections and again increase the throughput to the maximum. Okay, so there's some more factors which affects the throughput, and one very important factor is the packet loss in the network. So since there are two methods of whenever there is a packet loss and whenever we don't receive ACK, then the TCP has to retransmit it, and there are two methods to do this. One is go back N retransmission. For example, we have this buffer. For example, we have say it has a capacity of 43 MTUs, that is 43 TCP packets, and we transmit say up to 40, and we do not receive an ACK for 39. Then this go back N will have to go back from the beginning of the buffer and again retransmit the whole buffer again. So this will cause the throughput to drastically reduce and also utilize the bandwidth unnecessarily. So you can see some of the how very less packet loss, like 0.1%, can have effects of very high reduction in the TCP throughput. For example, 1% can cause the TCP throughput. If the packet loss is 1%, then maybe the retransmission itself takes 90%, and TCP throughput can reduce to less than 10%, the effective throughput. So yes, because when there is 1% packet loss, then the probability that when there are 42 packets in flight, the probability that any one packet can be lost can be very high, can go up to 1. So this really reduces the throughput a lot. And there are some schemes to mitigate this very high effect of packet loss, and that one of them is the selective repeat retransmissions. So as we talked in the previous slide, so if for example there are 44 bytes in flight, 44 packets in flight, and any one is dropped, in the go back N retransmission we have to retransmit almost depending on where it has been dropped, we may have to retransmit the whole buffer again. but in case of selective repeat retransmission, the server will particularly use a method called selective acknowledgement, and will tell exactly which packet is lost. So in this case, for example, if packet number 5 is lost, then it will indicate to us that I have received 1 to 44, but only 5 is I have not received. So the client side will retransmit only 5. It only selectively repeats the retransmission. So this will greatly improve the throughput. For example, in these example figures, we can see that even for 1% loss, this is like linear increase with the packet loss. 1% will give almost like 95% throughput.
Yeah, thank you, Prasad. Thank you for that. So this slide here, we're going to actually get into what is the recommendation for RFC-6349 testing. So what are the steps to actually perform this testing, which our ExpertTCP does. There are basically 3 steps that get run. They're condensed to these 3. We'll get into a little bit more detail within each of these steps, what the details of that shortly. But these are the 3 steps. First, we have to discover the MTU of the path between A and B. So what's the maximum packet size that can successfully traverse the network? That's a question. So we have to discover that. Typically, 1,500 bytes is where we're at with these modern networks. Number 2, what is the round trip time? You heard Prasad talk about the round trip time in some of his diagrams, and that affected things, of course. So what is that? So we have a method, again, recommended in the RFC to discover that, and we have to do that. That's step number 2. Then at that point, you can do your TCP throughput testing. You can do your complete measurement testing of the RFC and provide the results. And our GL's ExpertTCP, the note at the bottom, provides reports and graphs for all of these results. Okay, let's move on. So before we get into some of the details of these 3 steps, we have a couple slides on each step that will show you how that's done. It's very interesting on how that's done. We're going to first just tell you a little bit about what hardware we're talking about here at GL Communications that runs this ExpertTCP. And if you're familiar with GL's products, we have something called a PacketExpert platform, I'll call it. And that consists of a couple different hardware units, which I'll show on the next slide. But here this is basically how the test setup is run. Our product is controlled via USB, so it has a host computer running the software. And you have one of these guys on both sides of your network. And the client side, on the left-hand side of our diagram, is basically in charge of setting up the test configurations and so forth. So that's kind of the control of it. It manages the test. The server side on the right-hand side receives these commands from the client and does a lot of the measurements throughout the testing. Both sides are doing that, and is responsible for sending these results back to the client. So this is just a pictorial of that. In general testing, you want to isolate your testing network from your management network. So that's what we're showing here. Okay. So in application performance, general diagram here, no test equipment involved, but you've got clients on the left-hand side and hosts on the right-hand side. So, a host is, what we're talking about is, a web server, like the Amazon web server, the Google one, maybe an FTP site sitting somewhere. The clients are your browsers, your customer browsers, an FTP client, so forth. So, just a general network there that we're showing, and the next slide basically replaces, with our hardware, replaces that client and that server side. Again, this is where we've introduced our test equipment, replacing those. And we're going to be able to, with our test equipment, with our RFC testing here, with our ExpertTCP testing, we're going to be able to test multiple services at the same time, multiple streams, up to 16. Replaces the clients, as I said, replaces the hosts. So as this is happening and as we're doing these tests, and what I was mentioning earlier, we're going to be determining the maximum MTU of the network, the RTT, and then the true TCP throughput. Congestion, of course, in a live network is getting introduced. So we're going to show you how congestion can be, can describe many different things, packet loss, delays, things of that nature. How that affects this TCP throughput on the subsequent slides here. One more. As I was mentioning, our hardware platforms at GL Communications that run this ExpertTCP are based on something we call PacketExpert. Now we have, on the right-hand side, we have our traditional, it's been around for quite a while now, it's PacketExpert 1G, we call it. It's a 4-port PacketExpert. It is still in operation, it is still being sold by GL. On the left-hand side is sort of our next generation. It's being sold now, and it incorporates 1G ports, 1 gig ports, as well as 10 gig. So this can be used in either a standalone manner where you hook it up via USB to a laptop computer or a host computer, or we have a tablet version of the same thing. So on our 1G, on our 1G we have it's a 4-port tester. For this ExpertTCP test, we're using actually ports 2 and 3 to do that, and it's a copper port or an optical port are the options there. And with our latest hardware, the 10G we call it, it also has it incorporates 2 ports for 10G testing, as well as a traditional. We got a 1 gig testing ports as well. So it's kind of the best of both of those. So this will be our platform for the future, I will say. It's going to incorporate 10G and 1G going forward. So at this point in the demo, what we'd like to show you is get into a little bit more details about these different steps that I was talking about to ultimately get to measuring your TCP throughput. And I'd like to invite someone to help me speak about that. Chandra and Vijay will be helping with. So I'll hand it over to them to describe the next few slides.
Okay, this is Chandra. Actually, as we discussed earlier, the TCP throughput measurement is involved in 3 steps. One is path MTU discovery. This is that it discovers the MTU, maximum transmission unit, from end to end. And usually they will use, in traditional networks, they use 1500 bytes. Okay, and so we have a mechanism in our TCP, expert TCP. So we can set MTU as maximum, and we with the don't fragment bit set, and we send through that. If we get and we will wait up to transmission RTO timeout. If it doesn't receive, then we lower it with binary search algorithm, and we find out the MTU, that where it will pass from end to end, A to B. That is our first step. Okay, this how it looks, that the path MTU discovery. When you see it, it has MTU means it contains IP header, 20 bytes IP header, and TCP header, 20 bytes, and payload, that is MSS. These are the typical terms used in TCP. What is the TCP segment, IP datagram, and maximum segment size. And actually this path MTU discovery is, we are determining based on that RFC-2544 packetization layer path MTU discovery. Okay, so other the important step is here is the RTT measurement, timestamp based RTT measurement. So in this we have special option fields in TCP. So we are using that option to set that the timestamp value. We are having the internal timer. When we send the packet, we set that timer. The timer is very accurate. It was running at 8 nanosecond. This one increment in steps. So we load that when we send the packet, say value 50 to the other end. So other end, it's swap that and it sends it back, and then we get that value, and then what is the current time. Based on that, we measure what is the round trip time exactly. So our next slide is ready to measure TCP throughput. How this congestion window and receive window it was. Slow start and congestion avoidance. Actually, when you see that it starts from slow start, it sends the one packet. Once we get the acknowledge, it doubles, and once to get the corresponding acknowledge, it doubles, and once it reaches the threshold, that's what the other side, whatever the advertised by that, then it set the congestion window to that size, and then afterwards it maintains that this one, the packets. So then afterwards, based on that receive side, how it advertises, based on that it sends the packets to the other side. Okay, this is that. So what we use that algorithm. So when it sends the one segment until once it reaches the threshold, suppose in a pipe, suppose if we have 64 packets, then it advertised by the other side, remote side. It says that suppose if timer occurs, then it gradually decreases, and then once again it starts the slow start and set the window size to half, and it fires the packets. And once if you get a duplicate hash and until the timeout, so it happens, then once again this steps will repeat. Then once again it reduces that, so that it will be halves that. Then once again it starts, and if there is no congestion, it increases gradually.
Yeah, hi, Chandra. Can I add a few points there?
Yeah, sure.
Okay, so well, one of the things that I think Chandra mentioned, but maybe quickly, path MTU Discovery, the way it's done is using this do not fragment bit, which is in the IP header, I believe. Prasad, am I right about that?
Yes, ma'am.
Okay, so essentially the IP, it's telling the network, which is at the IP layer, do not fragment this packet. And if the network components pay attention to that bit, or if they'll attempt to send that packet, in this case it's a 1500 maximum size 1500 packet, 1500 byte packet, the network device will attempt to send it, but if it can't, it will drop that packet. And of course, if it drops it, the packet does not reach the endpoint, which in this case is the ExpertTCP server. And if it doesn't receive it, it will not acknowledge it. So the lack of acknowledgement at the client side is an indication to the PacketExpert client that it needs to possibly reduce the size of the packet. And it will use some sort of a binary algorithm. Instead of sending a 1500 byte packet, it might send half that, 800 byte packet, and see if that goes through. And then if it does, then he'll again add half more, like instead of adding, he'll add 200 more, and he'll get to 10,000, and so on. So we'll actually achieve the number that is required, the actual size, through some sort of a binary search mechanism. But it'll first try 1500. Normally this will probably work in today's networks. As Matt had said, these are modern networks. I think they all are capable of handling the maximum packet size. So I just wanted to mention how we actually do that. we rely on the TCP ACK from the far end as confirmation that the packet went through all the way. So it's a direct confirmation. Okay, could we go to step 2, Chandra? Okay, so here I think Chandra explained exactly how it's done. Initially, the sender has a timestamp of 50. He puts that into the packet, sends it to the far end. The far end takes that same value, sends it back, and so now the sender has access to the time that he sent the packet as well as the time that it was received. In this case, 150 was the time that it was received. The time that it was sent was 50 by virtue of the fact that that's the value that's in that packet, as you can see that. And then, of course, the subtraction is easy, and you do this repetitively over multiple seconds, and it really ends up being hundreds, perhaps thousands of packets. So you get an average, and that average is used as the nominal RTT measurement for step 2, which is used in step 3. Okay, so can you go to step 3? Okay, so this, so what Chandra was trying to say here about there's a 2-step or a 2-phase process for measuring TCP throughput. One is called slow start, and it's a process where you try to rapidly find out how much the network can handle in terms of bandwidth, packets per second. And then when it reaches that, it gets into this congestion avoidance phase where it tries to slow down the transmission at that point to maintain that so that it achieves some kind of TCP equilibrium. Now, it's possible that during any of those phases, you could get packet errors, so they can cycle through these 2 phases as we go through this process of measuring TCP throughput. For the next slide. Okay, so Chandra explained this to you. This is the slow start process where we're geometrically increasing, doubling the packets to determine where the network bottleneck might be. Okay, the next slide. So this is the process. This one is a somewhat complicated graph, and what we're trying to show here is at the very beginning is called the slow start process, where we're sending 1 packet, then 2, then 4, and 8, and 16, and so on. So that is what we call the CWND, or the congestion window. So that is the sender sends according to that value that he's maintaining and incrementing. As long as he gets back the acknowledgments for those packets that he sent, he continues to double the number of packets that he's sending. Now, he's eventually, obviously, going to reach a threshold where he won't get the acknowledgments, or the acknowledgments, or some packets will be lost, or he might get duplicate ACKs, which is, again, an indication that somewhere some packet was lost. So when that occurs, when that timeout occurs at that peak, he then decides he drops the CWND window all the way down back to 1, but he also halves the threshold. See, initially the threshold was 64 over in the upper left-hand corner there. It was set at 64. Once you had the timeout, the threshold is now set to 32 in the middle there. And now the threshold is set at half, but we're starting over with the slow the slow start. And so again, so we have actually in this graph, you can see the slow start. There are several attempts at the slow start at the very beginning, in the middle, and also towards the end there. We're still in the slow start. So we can get into the slow start multiple times depending on how often you experience congestion. When you're in the slow start phase and you exceed this SS threshold, SS stands for slow start threshold, but it's the number that's being adjusted as a function of congestion. So once you exceed that slow start threshold right there in the middle, in the second slow start phase, we exceeded the threshold of 32. Once you exceed that, you slow down the transmission of packets. and you keep it sort of level, or you increase it by a nominal amount, which is 1 packet. And then again, you're waiting for some duplicate acts or a timeout to indicate to you that the network is perhaps you're reaching a congestion point. But certainly you found this out very rapidly by initially this doubling process, coming back down, lowering the threshold, and then again achieving this threshold. So this is the method by which TCP throughput is measured, or we acquire the statistics in this manner. And we'll now show you how it's actually done with actual software screens.
Yeah, okay, thank you, Vijay, for doing that. So what we've done with respect to the time here, we don't want to go too long for you, but what we've done is we wanted to devote most of this webinar to explaining the operation and how it kind of works behind the scenes there with the algorithms and so forth. But what we've also done here is we've put together some screenshots for you of our actual software, our ExpertTCP software that we'd like to go over with you. And if I could, Prasad, would you scroll through these for us in fairly quick manner, if you would, just to show some of the different screenshots that our ExpertTCP software and hardware looks like for us. And I can help you scroll through them, but if you would commentate on what these are for us.
So this is, we have already seen this. Matt has explained this. So here we have the laptops, client and server side, controlling hosts, communicating over the different network than the network under test, so that we don't mix them. And server keeps updating the statistics at runtime to the client, and everything is controlled through the client. So what all the screenshots you'll see from now on will be on the client side. Okay, so this is the main software in line with all our other applications over PacketExpert. This has a similar look and feel. We have a menu option, a menu tree option to the left, and the various screens, multiple views in the main pane. Okay, so while we took the screenshots, we did setup to run a test, and then took the screenshots. So the setup is like this. Instead of having a network, we are using our PacketExpert IP link sim, which is a WAN emulator, which can emulate the typical impairments or delays or bandwidth that typically found in wide area network links. So we've connected the client to one port of IP link sim and the server side to another port, and it passes the traffic through it while introducing impairments. So we introduced say 25 milliseconds in one direction and 25 milliseconds in other direction, totaling to 50 milliseconds. So the RTT we emulated was 50 milliseconds in this.
Okay, very good. So yeah, just to sum that up, the subsequent slides that we're going to show are the screenshots from this test setup, where we're simulating a network or emulating a network here, a real-world network in the middle. Okay, go ahead.
Okay, so these are the screens to do the basic network setup. So first thing we need to do is connect to the server. So the remote side server, this is a very simple configuration. All we have to do is enter the IP address and say connect, and then we can set up the interfaces, the physical interfaces, and we can set the link speed 1000 Mbps, and then after that we can configure these are all on the client side. We can configure the various addresses, MAC address. You can use either user can define his own or the default one. So user can enter the IP address, the subnet mask default gateway, and user can also enter the bandwidth of the network in between. So depending on what the network provides. So either we have provided option is there to enter different bandwidths for upstream and downstream, because typically the networks will be asymmetrical. or in this case both are same. So in the TCP setup, user can configure in the 1G platform 1 to 8 TCP connections, and in the 10G platform up to 16 TCP connections. So here there are two screenshots showing those setup. User can do automatic, in which case the ports are selected automatically, or he can select manual and change the ports. Yeah, this is a test setup, and here there are various options here. So one of the important features is the test can be conducted either single direction, upstream or downstream, or bidirectional, like both upstream and downstream are conducted simultaneously. And the user can specify the transfer size. So this determines the duration of the test, how long the test will run. And these are the 3 steps that we talked about earlier. So the user can choose to run, let's say the first step will be a path MTU test. So user can either choose to run it, or he can enter different upstream and downstream path MTUs manually if it is already known. Similarly, the second step, that is the baseline RTT or the nominal RTT, which we run before the throughput test. So either user can choose to run it or can enter it manually, and then the throughput test will be run, the third step. Okay, and while running there are certain status displayed here. One is the overall status and the status of each step and the connection status, and the path MTU results, the baseline RTT results are displayed. So we display average RTT, min, max, and the baseline RTT selected will be the minimum found during the test. And we also display a brief summary of the various parameters which we use for the TCP throughput test, the third step. So baseline RTT, and we display what is the BDP which we calculate, but what is the actual TCP window which we use during the test, because here we have selected a single test, so we have limited it to maximum of 64 KB, even though the BDP is 625 KB. So we'll only simply use 64 KB and various other parameters like the MSS, the transfer size. And while the test is running, we display a series of statistics. This is per connection, like the time elapsed, the transmitted frames, the transmitted bytes, and if there are any retransmitted frames or bytes, and the percentage of retransmitted frames. These are updated every second. And the throughput results, the average, min and max throughput, and the RTT results. Again, these are all calculated and updated every 1 second. And we display this final results where we show the actual throughput and the ideal throughput. So the ideal throughput is according to RFC-6349, and that is calculated based on the line rate. So here the line rate is say the network bandwidth is 100 Mbps. Then the maximum possible TCP throughput is 94.143. But since we used only one connection, and it is around, we are using a buffer of around 10% of that, so we are getting around 10% bandwidth here, maximum TCP throughput, which we measured. And we also display the exact time down to milliseconds, the transfer time, the time it took to transfer 100 megabytes of data, and compare it to the ideal transfer time. The ideal transfer time is the time taken using this ideal throughput, and the transfer time ratio is a measure of how much the actual transfer time is greater than the ideal transfer time. Ideal, the perfect would be the value of 1. And we also display the TCP metrics defined by RFC-6349. The TCP efficiency is the measure of transmitted bytes compared to the retransmitted. So here there were no retransmissions, so it is efficiency is 100%, and buffer delay is measure of how much RTT increases during the actual thread test compared to the baseline RTT. So there was a slight, very slight increase in the measured RTT. So we have a buffer delay of 0.006%. And we also have some graph display. We plot it continuously at runtime. So we have throughput graph, throughput in Mbps versus time. And this we have captured with introducing 0.1% packet loss. As you can see, the throughput is continuously keeps varying. It reaches a peak and drops down. So to know the reason why, we also have this throughput versus retransmitted frames plot. There is a two y-axis graph. On the left hand side we have throughput in Mbps in blue, and the retransmitted frames are also plotted. This is the scale is on the right hand side. So this graph shows what is affecting the throughput. So usually throughput is affected by either retransmissions or the RTT changes. So in this case, we can immediately see that the retransmissions are happening, and whenever the retransmissions dips, the throughput increases, and whenever retransmission happens, that takes priority and the throughput suffers because of that. And now one more example we have is previously I showed screenshots of single connections, but if we run say up to 8 connections, then we can increase the window size and corresponding bandwidth. For example, here we have run with 8 connections, and the TCP window was we could manage was 64 KB into 8, that is 524280, and this window is distributed among all 8 connections. So with that, we get this is per connection. So connection 1, we get 10.3 Mbps. Again, connection 8 also we get 10.3 Mbps. So we plot the throughput graph individually. User can select the connection and view the graph per connection. So with this 8 connections, we see improved throughput. So the actual throughput now has gone up from 10 to around 81. That is 8 times increase. And transfer time ratio and have improved very much. Buffer delay is almost the same because RTT remains the same. Yeah, we have a video showing this. So I'll just go through this quickly.
Okay.
So yeah, this is a basic software as I talked about, and we first run the server side. Server side, there is no GUI, it's just a application, the server application. So we just start that, and we come back to the client. And here we enter the server's IP address, and we connect to it. Okay, so we connect and we wait for it to connect. Okay, so once it is connected, we go and verify the ports. We see that it is everything is connected, and this setup is similar to whatever I talked about. So we have an IP link SIM in between. The client is connected to port 2 of IP link SIM, and server is connected to port 3. So we now go to IP link SIM, and we introduce the characteristics of the WAN. So we'll put a latency of 25 milliseconds each direction. So total is 50 milliseconds. So we verify the ports are connected, and then we go and start it. So now we have the emulation setup. So now we go back to the TCP, and we do the network setup. So we just use the default MAC addresses, and we have configured the IP addresses. These are the test IP addresses, and we configure the upstream and downstream CIRs, which in this case we are configuring to 100 Mbps. And then we'll do the TCP setup. So we can have 1 to 8 connections. So we'll select 8 connections, and we can either configure manually or automatically. So we'll go with the automatic, and then we'll do the test setup. So in this setup, we'll just run an upstream test from client to server, and the transfer size can be megabytes or kilobytes. So we'll just transfer 100 megabytes, and we'll select the run throughput test, and the path MTU test. So user can enter manually, choose to skip this test, or run it. Similarly, baseline RTT. And then we'll start the test now. And so here we see the overall status here in this window. So the path MTU is done now, and baseline RTT is running. And we also show the connection status. So the path MTU results window can be accessed from here, shows that the result is 1500 bytes. Now baseline RTT test is running, and that is done now. So we'll just open the baseline RTT results, and it shows us the value of 50 milliseconds, and that is the trial duration in seconds. And we select the minimum out of it, so the selected value is 50.022 milliseconds. And now we see that throughput test is also done, and all the connections are closed. And now we'll go back to the test parameter summary which was used. So here the calculated BDP comes to around 625 kilobytes, but we are since we are using 8 connections, so we are using a total window size of around 52 kilobytes, and path MTU used is 1500, and a transfer size of 100 megabytes. So we'll see the throughput results. So it shows per connection. Sorry, I'll just go back a little bit. Okay, so here we have per connection results. So we can view for every connection. So the results are similar for each connection. And yeah, we have the graphs here. So we can view all together, or we can view individually, connecting the specific connection, selecting the connection. And for example, for 1 and 8 we can view separately, and we can change the duration of the graph. And we have statistics per connection, so it shows the transmitted frames and bytes. So this 100 megabytes is distributed among all the connections, and together they transfer 100 megabytes. Like the bandwidth, even the transfer size is shared. And here we have the actual throughput, which is around 82 Mbps. And So because we used a window size of less than the optimum, yeah, it's around 524 kbps, kilobytes. So we got less than optimal maximum throughput possible. And we have the transfer time and ideal transfer time. And the transfer time ratio is a little bit more than 1. And efficiency and buffer delay. So buffer delay was because of the difference in the RTT measured and the baseline RTT, which is 027 compared to 022. That's why we have a little bit buffer delay there. And we have this throughput versus RTT, which is constant in this case, around 9.4 versus 50 milliseconds. And we have throughput versus retransmitted, which is also constant in this case, because there was no retransmission, it is 0. And these are all again available for every connection. Now we'll go to IP-Link SIM and introduce 0.1% packet delay and see what happens. So we have maintained 50 millisecond delay, but introduced 0.1% in one direction. Now we will go ahead and start the test. So the path MTU is done, and we're waiting for the baseline RTT. So that is done, and throughput test has started. So yeah, we see the test parameters here. And because of the packet loss, we can see that the throughput is continuously varying for each stream. And if you see the throughput versus retransmitted graph, it will be more clear to us that whenever there are retransmissions, then throughput dips. And this is plotted for every connection. So we can see that the throughput result for every connection has come down. But RTT remains the same because the delay in the network is the same. So we can see that for every connection there are some percentage. For example, TCP connection has 3.5% retransmitted frames. 8 has 6.25. Like that, every connection has retransmitted frames. So yeah, so we can just view all the throughput graphs as a whole, or we can have view only, say, connection 1. So yeah, this shows the effect of retransmissions. This is only the throughput, whereas the bottom screen shows the throughput with retransmissions, and shows the variations here. So we can show similarly. We can show for for connection number 8. Every connection we can see the results. Okay, so the final results again, we see that it has dropped down from around 80 to 67, and actual transfer time has increased, as is the transfer time ratio, and efficiency has decreased because of the retransmissions. But buffer delay remains almost same because RTT has not increased. So RTT is a constant. So we see this buffer delays same.
Yeah, thank you for the demo, Prasad. I think at this point you kind of got a flavor for how our software is laid out if you haven't seen it before, and how you got a little background early on in our web. And I'm sorry that we've gone over the time, but we wanted to show you some theory, how it's running from a practical standpoint within our software. Now we can open it up, and if anybody has a question, if you would like to email us, it's very easy. You can go to our website and we can get you in touch with one of our experts to talk a little bit more about this. gl.com, very simple. Or you can just email a question to info@gl.com, and you can mention the webinar, and I got some more questions, and we'll get you to the right people. So info@gl.com. Yes, thank you. Thank you everyone for attending, and have a good day.